Welcome back to ECE 501B. Homework number 5 is due on Friday. Homework number 6 is due a week from today. And our second exam is a week from Wednesday, if I'm keeping track of the dates. And this is homecoming week, if you didn't know, which means that things get shuffled a little bit, but I won't be in office hours on Friday, on that Friday morning. Exam 2 material is posted, and you'll want to look at that for practice. I've also posted, and I don't remember when I did this, but the project material is now available to you. You've actually had access to some of the possible sources of where you can go for your project on the course resources module within D2L, but the project actually has 3 deliverables, and you can read about that. But the first deliverable is really just an exchange between you and I saying, will this work for the project? And if you don't hear back from me, the answer is a default yes. But if you hear back from me saying, wait, let's talk about this, then we need to proceed a little bit more. But number 1 deliverable, that's what that means, is due, I think, before the Thanksgiving recess. Just so that you now are focused on what you need to be doing for your project for the remainder of the semester. Then number 3 deliverable is a reflective paragraph. That's a short piece deliverable, but the second deliverable is the majority of your project, and that's described in that handout or in the description. Here are some possible sources for that project. Not the first one. Signal theory is really the textbook. I guess you could do something on infinite dimensional vector spaces using that textbook, but the main papers, the project can be a reading of a paper and answering or essentially filling in gaps or helping explain the material in that paper to someone of your peers, someone that has taken this class. Can you now provide background or additional information in it to extend the ideas in the paper, or to fill in the ideas in the paper so that a peer of yours in this class could read that paper more efficiently. They could read it without struggling as much as what you might have when you first read it. The first one, the $25 billion eigenvector, which is about Google and the search engine, that kind of gives you an idea of how you could do it. They write this paper in a fairly educational way, meaning occasionally they will insert, oh, here's a question, or here's a challenge, or here's something to look at based on what you've already read so far in this paper that will actually help you progress further into the paper. It now fills in a little bit of the information. So in that $25 billion eigenvector paper, there might be 11 or more questions that you could answer, and that could sort of be your project. But if you wanted to study a different paper, then you could maybe use that as an example as to how, and I would encourage everyone to quickly read maybe all of the first 3, maybe not all of the 3 chapters of Penrose, but you can read the football ranking. That was based on the Bowl Championship Series. How do you compare teams that maybe don't play each other, and there's 125 teams, so they don't match up team to team, but can we actually rank these based on, in aggregate, everybody playing about 10 or 11 games in the season? That's the football ranking, and all of these are using concepts from the class, and I try to describe just briefly in the location where you would find these papers that information as far as, oh, this might be dealing with positive matrices, or this might, obviously the eigenvector is dealing with eigenvalues and eigenvectors, or you can see that coming in. Principal component analysis is a tutorial paper. Again, you could apply that to a pet project or something that you're interested in, or you could simply examine that paper itself and answer questions or try to fill in the gaps that you think would help a peer in reading that paper. The Road to Reality is written by Penrose, and we'll maybe talk about the Moore Penrose inverse, but it kind of takes you on a journey in terms of starting from the real numbers and then progressing to, well, actually it doesn't start with the real numbers, it starts with the counting numbers, and then you just naturally go through the progression up to complex, and then you start doing Pythagorean Theorem, etc. But that's an interesting history or explanation of reality. He's taking you on the road to reality, so read that with that intent. Today what I want to do is recap orthogonal projection. If we haven't yet talked about it in class, the orthogonalization lecture is now available for you on D2L. We will then talk about vector space direct sum decomposition when we do this orthogonal projection. We'll talk about the properties of an of a projection operator, and that actually leads us to the ability to do minimization problems. And minimization problems typically are asked, or you might be expected to examine or apply or perform some kind of minimization problem, and now you have some tools to think about it from a linear algebra perspective. We've talked about linear functionals, but we want to review those a little bit so that we can talk more thoroughly about operators on inner product spaces, which is chapter 7, and so don't disappear or fall asleep, but that material will not be on exam number 2. Exam 2 will stop at chapter 6, content-wise, but we are going to move forward, and we will be doing chapter 7 material prior to exam number 2. And the first thing that we'll talk about is this concept of an adjoint or T-dagger. That's supposed to be a dagger symbol on the superscript of T, and I believe the author actually uses a star, but you know me and stars, so I'm not that good with stars, but those are complex conjugate in this class. Orthogonal projection, recap. Suppose we have a subset of a vector space V. Then we can actually define U perp, and that's what the superscript on U, this is a capital U, is trying to indicate. U perp, or U perpendicular, that's the way you can think about it. U perp is the set of all vectors in your original vector space that are using the inner product orthogonal to all vectors in the subset U. U does not have to actually be a subspace. U can be a subset. U perp is perpendicular to these vectors or these points in the subset of capital U. Even though we start with U being a subset, U perp is a subspace. So even though we are starting potentially, we'll mostly deal with U being a subspace, but it could just be a subset. One way to think about it, let's say we had the XY plane as capital V. Then let's say a subset U might be the small line segment in the x direction from 0 to 3. That's not the x-axis. That's a subset. But you can find vectors v in the two-dimensional space that are orthogonal to that line segment. Essentially, they're vectors that are in the vertical direction or in the y direction. And those do form a subspace because the 0 vector is always orthogonal to everything. So you have the 0 element in U perp, and you can show that you have linear combinations are closed, or this U perp is closed to linear combinations of vectors in that subspace, or it's closed under addition and scalar multiplication. So U perp is, I like to just think of the xy plane, or maybe you want to be three-dimensional. Now you can think of one vector or a line in that space, and what are the vectors that are perpendicular to that. If you had, for example, 3 space, and you had a vector, a line is U, then what you would be looking at is a plane going through the origin that's orthogonal or perpendicular to that line. That would be U perp. And U perp are obviously orthogonal, and we can then think of separating things according to U and U perp.
So a line at x equals 3 contains 0 element?
So the line segment that I used before does contain the 0 element, but it wouldn't have to. We could have had a line segment from 1 to 3. And there's a subset. You can now have vectors that are orthogonal to that, and it doesn't contain the 0 element. I just was saying 0 to 3 so we could quickly think what that was. But for a subspace, it has to be, here I'm pointing, and you can really see if you're listening to this, but it has to be containing the 0 element, a subspace, and it has to be closed under addition and scalar multiplication. And if you now just have a line segment, that's not necessarily closed. You could have 2 elements from that line segment going outside of that line segment. So it's no longer closed under addition. I don't know that I repeated the question, but the question was, I thought 0, 3 does contain the 0 element. Yes, it does, but you could have a line segment that is a subset, or you could have the integers even along on the x direction. That's a subset, and you could now be orthogonal to that. If U is a subspace, so now let's say it is the x-axis, then we can decompose V into a direct sum of U with U perp, which means that we can now find unique vectors in U and U perp to create or represent any vector in capital V in our xy plane. Here I'm just going to read this, and you have it available to you, obviously. But here, when U is a subspace, then the direct sum representation of V implies that there's a unique representation of any or all vectors in the vector space V in terms of those orthogonal subspaces. So you can find a vector in big U. You can find a vector in U perp to create any little vector V in the big space, vector space, capital V. So can we have more than 2 orthogonal subspaces? We actually are dealing with just 2 in this case. So in the way that we're doing it in defining U and U perp, no, those are the only two subspaces that we, or subset and subspace, we want to deal with. We're only splitting things up into halves. So here, you give me a V, we can now decompose that V into one component that's in U and the other component W in U perp. And this now gives us a nice way of projecting onto our original vector space U from any element vector in V, or any vector in big V. And that's called this projection operator. So we will use this feature to define a projection operator, which we're calling now capital P sub capital U. And capital P sub U is an orthogonal projection of a vector V onto U. So if we had a 3 space, let's say this room, and now the xy plane is the floor, and somebody draws a vector from one corner of the room, the origin, out in space, this projection operator is projecting the end of that vector down onto the floor, perpendicular. That's a visual maybe to keep in mind when we're thinking about this orthogonal projection, or this projection operator. So that now for all for all V in our original vector space V, we can decompose that vector into one component that's in our subspace U and another component that goes up to the end or the tip of that vector, and that vector would be in U perp. And we define this projection of V through P sub U that will equal a vector on the floor or in our subspace U. So this projection of a vector in 3 space onto 2 space is going to be projecting now onto 2 space, so U does belong to our subspace U. That's what that's saying. What are some properties of the projection operator? And here again, this is an operator, and what's an operator? And my capital U's and lowercase u's are hard maybe to distinguish, but hopefully it's clear that this is now P, capital P sub capital U is now a linear operator on the vector space V. So the input vector space and the output vector space are the same. One property of this projection operator is that the range of the projection of U is U. You can now fill the whole space. You can have that arrow or that vector pointing in all sorts of different directions, but that then says that the tip, when you project down from it, will fill the entire two-dimensional plane. Question? So we are projecting V, this is the little vector V, onto the subspace U. The input is V, it's a linear operator, but we now have a vector V, so just think of this as a way of decomposing that vector V into 2 pieces. One piece is in the subspace U and the other piece is in the perp. And so now you essentially have a triangle. and the hypotenuse is V, and the triangle is the two orthogonal legs or sides of that triangle. So you give me a vector V and another vector V, you can show that that operator will be linear. So it satisfies linearity properties. The linear combination of vectors that are operated on by P sub u will be those linear scaled versions of P on each of the individual components of the V's, or the V1, V2, etc. So the first property is that the range of this operator is the subspace U. Another property, if we're dealing with range, we might as well look at the null space. The null space of that projection operator is orthogonal to the range, or it's equal to U perp. So you give me a vector in U perp, you project that down onto U, the only place you're going to go is the 0 vector. Since you're starting with a vector that's orthogonal to U, projecting it to U will get you nowhere. It'll get you to the 0 vector. Also, if you take V, any vector, and you take away the projection of V onto U, where is that going to be? Where's that an element of? Or you could say, or you can start to kind of see maybe where these are. Where does this put you? That puts you in a U, right? A little U. And now you're taking that apart away from V, and this is now a W. And where does W live? That's in the orthogonal, that's in U perp. So this is now in U perp, and that's true for all V in your vector space. Another property is if you simply operate on it again, what's it going to do? If you project twice, essentially, what's, pardon? So it's basically identical to just one projection, right? So now you project again, you're back to where you projected the first time. You're not going to do anything different with the second projection. Final, well, one more property. This, I think there are more listed in the book. Here, the norm of the projection of V onto U is less than or equal to the norm of V. And I think you can see that by, there's my people again. I didn't know I had any people. This is true for all vectors V in V. And there you could think of, oh, here's my three-dimensional room. The hypotenuse, its length, is bigger than one of the sides. That's essentially what you're saying here. Where the hypotenuse is V and you're projecting on one of the sides, that's what's on the left-hand side. That projection of V onto U is going to be in the subspace U. And that vector is going to be having a length or a norm less than the original vector V. We can also actually create this projection fairly cleanly. And it's by using the orthogonalization material that we've learned. So also we can use let's say our results from earlier. Suppose that we have a list E1, E2 up to E sub m of vectors, and that list is actually an orthonormal basis of U, or basis on U. So you give me a basis, a list of basis vectors on U. You can find an orthonormal set or list from that. So you now have an orthonormal basis on U, and that's now given by these vectors E1, E2 through E sub m. Then the orthogonal projection of V onto U can be found by looking at or taking a scalar, which is found by projecting V onto E1, and then that scales the E1 vector, plus V onto E2, project V into that direction, and then use that to weight E2. And we can just keep doing that until we run out of our vectors. And that's equation 39 in chapter 6. So if somebody wants to find this projection, this orthogonal projection of V onto U, what you can say is, well, give me a basis of U. Then you can orthonormalize that basis. Now you have E's, E1 through E sub m. We're assuming what? That U is m-dimensional. Then we can find the projection of V onto U using this formula. And that now leads us naturally into minimization problems. Or we often run into problems that can be cast in the following form. Suppose we're now given a subspace. So U is a subspace of V. And suppose now somebody hands you a vector, little vector in V. Now the minimization problem is actually to find a vector U in the subspace big U such that the length of the vector V minus U, or the difference between V and U in a norm, is minimized. Or we want to find U that is closest to V, where U is in our subspace capital U. Here is another, it's back to our room with our vector sticking out of the corner, which is the corner is the origin. Somebody now gives you a vector in your room and they say, oh, minimize the vector on the floor, or find the vector on the floor that's closest to the tip of that vector v. Well, what do? You run right underneath the tip of that vector and stand there on the floor and you go, I'm the minimum u, because you're now projecting down orthogonal from v, and now you've minimized the distance, or the length, or the size of that distance between v and u. Suppose I'm standing right under the tip of that vector capital or little v, and somebody else goes, I am, and they're somewhere other than where I'm standing. Now you measure the distance from their feet to the tip, and you measure the distance from my feet to the tip, and which one is shorter? Do you see what I'm trying to get you to visualize? So that's really all that we're saying here. And we're going to use orthogonal projection to make that happen. Orthogonal projection gives us just the tool to perform the above minimization, or to do the above. And that's in the form of a proposition. Proposition 56 is labeled as minimizing the distance to a subspace and that's really what you're doing when you're running underneath the tip of that vector v. So that's the label, minimizing the distance to a subspace, and here's the proposition. If capital U is a subspace, of this vector space V, and little v is some vector in that vector space, then the norm of V minus the projection of V onto U is less than or equal to the norm of V minus U for all U in the subspace capital U. So this is basically the projection of V onto U. That's where I was standing. And anybody else on the floor is the little u on the right-hand side. And the only time when equality is true is when somebody's standing exactly on top of me or at the same location as where I am. Otherwise, their norm is bigger than the norm from my feet to the tip of the vector V. That's what I'm trying to say. If we have equality, meaning if this norm on the left is equal to the norm on the right, then in fact the u that's on the right is equal to the that's where I'm standing. That's equal to the orthogonal projection of V onto U. That's what happens with equality. Now, let's see if we can prove this. And you're going to probably start scratching your head at this proof, but it looks weird, but it's pretty straightforward. Okay? So let's now say we're given an arbitrary u in the subspace capital U. then find the norm of V minus the projection of V onto U. And let's just, it's easier to work usually with squared norms. That's less than or equal to what I just wrote. You'll buy that, right? You would buy this for sure, right? What if I add something positive to the right-hand side? Then I can do that. And the something positive that I'm going to add to the right-hand side is going to be projection of V, the orthogonal projection of V onto U minus U. So where is this as a vector? What is this? This is V, the tip of the vector, minus the vector that's below it in the subspace U. So it's now in U perp, isn't it? So this is now an element of U perp. Where is this? What's the projection of V onto U? Where is that? U minus a vector in U, and that's a subspace, so it's what? Closed under addition. So this is now in U. Right? So if we say that this is, and do you see why it's less than or equal to? I've just added a positive amount on to the end of that. So if I call this A and this is B, I'm getting at really A squared plus B squared is equal to C squared. So now I can say that this is less than or equal to what? C squared. Since Pythagorean Theorem is still true and C squared is A plus B, so here is A plus B and this now, if I have what? A and B are orthogonal, so I can use the Pythagorean theorem. There's A squared plus B squared is equal to C squared. This is now using the Pythagorean theorem. But what is that C inside the norm? Can I clean that up any? I have minus something plus that same something, so that goes away. And I'm left with V minus U squared. And that's what I set out to show. That what was on the left, the norm of V minus the projection of V onto U is less than or equal to V minus U for any U in the subspace capital U. And again, the picture that you can think of for that is what I've been trying to indicate all along. As a way to interpret this geometrically. If I now have a subspace U and somebody now gives me a vector V, I now want to think about, that's supposed to be an orthogonal projection and that's supposed to be a right angle. This vector, if this is V and this vector is what? let's call it U star because I wanted to use a star today, I guess. But that's now the orthogonal projection of V onto U. I've projected down from V onto U, and what is this vector here? If I went from U star up to V, that's going to be V minus U star. And this, let's say, is some W, and that's in U perp. Where this is the closest point in my subspace U to V. If somebody moves away from that tip of the arrow on U, do you see that the length of that line is going to be longer than W, as I've written here? And it's not perpendicular, is it? So now any place along U, I can get to V, but it's not perpendicular, and so it's longer than that perpendicular projection. So the solution of general minimization problem is to take U star equal to the orthogonal projection of V onto U. And U is a subspace of V. Here I'm just saying it as a subset, but here we're saying subspace of V. And we know how to mechanically compute that, or compute it with an expression. But earlier, we saw if we had an orthonormal basis let's say on this subspace U, for example, E1, E2, E sub m, then using equation 39 in chapter 6 says that the orthogonal projection of V onto U is simply the inner product of V with E1 scaling E1, the inner product of V with E2 scaling E2, etc., and continuing until you've projected V onto all of those orthonormal vectors to scale each of those vectors by the appropriate scaled value determined from the inner product. So the strategy, this minimization strategy, is now the solution comes down to finding orthonormal basis on our subspace U, and then simply computing inner products. There's a way to find the solution to minimization problems, is using orthogonal projection. You might look at an example that is found in the textbook in Axler, page 199, and that's Axler has a good example involving finding polynomial approximation to sine of x. This is actually taking place in a function space, which is infinite dimensional, but it's still, I think you can understand it. So this actually takes place I know you can understand it. It's just a slight variation on what we've talked about so far. We've been dealing with finite dimensional vector spaces, but now this actually takes place in function space, but it actually drives home the point of how effective this approach can be versus just doing like a Taylor series expansion or some Fourier series expansion on, or Taylor series of sine of x. Look at the book, and there's two figures. One shows using this minimization strategy, and you can hardly see the difference between sine of x and its approximation between -1 and 1. And the other one, you use this expansion in powers of x that we typically would use, and at the tails the error is quite big. And with this approach the error is not that significant. So now let's look at linear functionals. We've seen those before. A linear functional, and we'll use inner products with these linear functionals. A linear functional on a vector space V is a linear map between the vector space V and the scalars, where the scalars are in our field of numbers, either real or complex. That's what we're meaning by scalars. So you're mapping from a vector space V onto scalars. If we pick a vector W in our vector space V, then if we look at the inner product of V with W, that will map any v into a scalar. That's what the inner product does. And this actually then is a linear functional. On our vector space V. That shouldn't come as any surprise. This is just a way to map a vector V onto scalars through the inner product. What's surprising is that you give me any other generic linear functional, and I can actually find a vector W that will replicate the one that you give me. So what's surprising is that for any linear functional, and I might denote that as phi on our vector space V, we can pick a vector W in the vector space V such that if we apply that linear functional to an arbitrary vector little v in our vector space capital V, we can actually find a W vector that we can put into our inner product with that same vector, and it's going to give us the same scalar out. And this actually gives rise to a theorem. In chapter 6, this is called the Reese representation theorem. And it goes as follows. Given a linear functional phi on our vector space V, then there is a unique vector, let's say u, in our vector space V such that the linear functional phi applied to V is equal to the inner product of that same V with u. And that's true for all vectors V in our vector space capital V. So let's prove that, or show why that's true. And to do that, let's first just define an orthonormal basis on our vector space V. And we'll parameterize that with vectors E1, E2, E sub n. So this is now an n-dimensional vector space capital V. Let E1 through En be an orthonormal basis on our vector space V. Then, if somebody now applies the original linear functional to the vector V, which I've now been using as a shorthand phi sub V, or phi sub V, then that's phi, and we have an orthonormal basis, so any vector V we can write as a linear combination of those basis vectors. E1 through E sub n. And the way that we will do that is we can now say, oh, take the inner product of V with E1, and that's going to scale E1. Do the same with E2. And keep doing that down to E sub n. And that is our original vector V. And this inside the big brackets is really just an orthonormal decomposition of that original vector V. And it's arbitrary. V is arbitrary. That's coming to us from our vector space V. So hopefully that's believable. And note what these are. Those are the result of an inner product, which is something in our field. These are scalars, aren't they? So all of these are scalars. And if those are scalars, then we can actually use, and what is phi? Phi is a linear functional. So now we can use the linearity property of our functional to slide those inner products or move that phi and apply it to each of these basis vectors. So on the first one, instead of phi of the inner product of VE1 with E1, slide that scalar out, and now we have that scalar scaling phi of E1, which we're just now calling phi sub E1 in our shorthand, if that makes any sense. So what I tried to say is this is now equal to VE1 phi of E1. And why is that? Well, this we're just using the linearity property of our functional. It was a linear functional. So now we have the same. We have VE2 with the linear functional applied to the second basis, or applied on the second basis vector E2. And we can continue to do that. V with E sub n, phi applied to E sub n. But what are these? That's the linear functional applied to each of our basis vectors. But what happens when we apply our linear functional to a vector? We get a scalar again. So these are now scalars. Different, but scalars. Well, now I'm going to start using a property of the inner product. And in particular, I'm going to use the conjugate homogeneity of the second slot. I'm going to slide those scalars into the second slot of my inner product. Meaning, and what happens when I do that? It's conjugate homogeneity, so I need to conjugate that linear functional. It's a scalar, but it could be complex. So now this is going to be V. Notation is what I just love. That's the star, right? E1 star E1. Phi sub E1 star E1. And this is due to the conjugate homogeneity of the second slot. That's where this next equality is coming from. And this is now, plus V phi sub E sub 2 conjugate E sub 2 plus V phi e sub n conjugate e sub n. Now I have a combination of a bunch of inner products, but what do I know about the second slot? What's the second slot enjoy? The first slot's the same. Can I somehow collapse this into one inner product? Because of what? Additivity of the second slot. So now I can form another equality based on additivity of the second slot, and now that says V is going to be in the first slot, but in the second slot I now have phi E1 conjugate E1 plus phi E sub E sub 2 conjugate E2, etc. This is the linear functional applied to each of those basis vectors and their conjugate, and they now form one vector, which in fact is the vector I was looking for. I said I could build you a U, and by construction there is my U. So phi sub this linear functional applied to V is equal to VU as long as U is as defined. It's the linear functional applied to the first basis vector. That'll give me a scalar. I need to conjugate that scalar. So that's phi sub E sub 1 star. That will scale E1 plus the functional applied to the second basis vector, conjugate that, etc. And that's how I will now create or construct my vector U that I said I could build. And now I can put that U into an inner product, and you hand me a V, I can give you the same scalar that somebody would have given you based on their original linear functional. I hope that this has convinced you that a U exists. Now what we have to do is it unique? We have its existence, now is it unique? So thus a U exists. Is it unique? And the nice thing is we now have the inner product, and that allows us to fairly quickly determine the uniqueness. So assume that this linear functional is applied to V, and let's say that somebody gets a U1 and I get a U sub 2. And they say, well, mine works, and I say, well, mine works, so they must be this equal. Now what we want to show, so we're assuming that now this is for all V. What we need to show is that U1 is equal to U sub 2. Well, if they're equal, then their difference will give us the 0 element, or the 0. So now a scalar. So now we have 0 is V inner product with U1 minus V inner product with U2. And that's true for all V. But we know additivity of the second slot works. And now we have that V inner product with U1 minus U2 gives us 0 for all V. Now we're scratching our head, but this is what we can use now, is we can say, oh, that's true for all v. Can I find a special v that will convince me that u1 is equal to u2? Well, if this is true for all v, why don't I just let v be u1 minus u2? It's true for all v. Why not make it a specific v? So therefore, consider a particular v that's equal to u1 minus u2. If v is u1 minus u2, then the inner product is u1 minus u2 with itself. But we said for all v, that is equal to 0. Now what can we do? So now we have the properness of our inner product, don't we? We know if we have a vector, inner product with itself, and that's equal to 0, what do we know is true about that vector? It has to be 0. So now by the definiteness property, of the inner product says that if I have the inner product of a vector A with itself, and that's equal to 0, the only time, that's if and only if, A is equal to 0. That's the definiteness property of our inner product. And that's what we are going to now rely on. Therefore, u1 minus u2 is 0. Well, that means then that u1 is equal to u2. So even though I had my u1 and you had your u2, they were the same. Therefore, u is unique. So it exists, and it's unique, and that's nice. So now you find yours however you want to find it. I find mine however I want to find it. It's going to be the same u. And that allows us now to compute these linear functionals using inner products. It's going to take a little work because what? We have to find an orthonormal basis of v, and then we have to apply that linear functional to all of those basis vectors and find the scalar, conjugate those, and then sum up the appropriate combinations of the vectors, orthonormal vectors, and that gives us our u. Exam number 2. That's the material up to this point. Okay? So now what we can do, we have a little bit of time, and I know you're just chomping at the bit to just keep going through the book. So we'll start a little bit on chapter 7. And chapter 7 is dealing with operators on an inner product space. Which means that we are going to be using what we've learned so far, so it's good review when we have to use some of this material. And the first thing that we're going to look at is this concept of an adjoint. And you may have seen this some other place in linear algebra, but don't think about that one. It's different than what we're talking about. Okay? So this adjoint is particular to this particular class. And this adjoint, we actually, in order to talk about it, we need 2 different inner product spaces. Suppose we have a linear map. We're not yet to operators, so we're just dealing with maps. That means that the input vector space and the output vector space could be different. So now we have a linear map between V and W. Here's our input vector space, and here is our output vector space. But we need inner products on each of those two vector spaces. So we need an inner product so this is going to be an inner product space, this V. Need an inner product space for all vectors little v in V. And we need an inner product space for vectors W that are in the big W. So we still haven't finished this sentence. We're still on the if clause. And let me just say that V and W are both finite dimensional inner product spaces over our field F. Now we can say the other thing. Then, so if we had a linear operator T, then T dagger. So this is now supposed to be a new symbol, and it's a dagger. And the textbook, Axler, he actually uses the star, which I've used for my complex conjugates, so it gets a little confusing maybe if you're jumping back between my notes and the book. But this is now the dagger is what I will use for the adjoint. So this T dagger is a map from the original output vector space W to the original input vector space V. Defined by pick a W and then given a linear functional phi on V such that this linear functional applied to V, which we could now say is TVW, and T dagger W is the vector in V such that the linear functional, that scalar, is equal to V. So much for what I wanted to say in Chapter 7, huh? Oh my, I better quit erasing. I've lost the whole lecture. But essentially what we're wanting to do, well, so much for that, is we wanted a linear operator that allowed us to move that linear operator between slots. So we had T in the first slot. We want that inner product, TV, comma W, to be the same. So we want TVW inner product to be the same as, the inner product of V with T dagger W. That's how we want to define T dagger. We want T dagger to be defined such that we can now change that linear operator between the slots. And I'm now frustrated enough, I'm going to say that's enough for today, and we'll pick up with chapter 7 afterwards.